this video we're going to look at isotopes and what that means. So an isotope is basically any element that has more or less neutrons. So if we add neutrons or we take neutrons from it, it becomes an isotope. Remember, the element is defined by its number of protons, so it never changes what it is. So adding and subtracting neutrons to an element doesn't change its element. It's still just hydrogen or helium, whatever it is, but it's now an isotope of that. A really common example that we see is something called heavy water. And you hear these terms particularly in nuclear reactors and things like that. So if we take plain old hydrogen, for example, and hydrogen looks a bit like this. Hydrogen is just plain old H11, has one proton, no neutrons. Plain old hydrogen. If I was to add another neutron to it, I would get this H12, or add a neutron. So it now has one neutron, one proton. I can go one further and say, let's add a third or a second neutron so that we have H13. These are still hydrogen, but these are isotopes of it. And so we actually name these. You may have heard of these. We've got hydrogen, which is our plain old basic element. We've got deuterium, which is our H2 isotope. And then, funnily enough, tri is the word for 3. We have tritium, which is the isotope for this. There's a shorthand way of writing this. So often when we see isotopes, and particularly in this course when we identify isotopes, they would write tritium as H3 or something like that. So you can write H3, or sometimes more commonly you'll see they'll write the full word. So hydrogen 3. Sometimes you see something like cobalt 16 maybe, things like that. So this notation here is telling you the isotope, so it's telling you its mass number. Hydrogen 3 has 3 protons and 3 neutrons. Cobalt 16 has 16 protons and neutrons, like combined, not individually. So you can then reverse engineer this and say, well, if I take my hydrogen 3, I know that hydrogen has 1 proton, but it's got 3 protons and neutrons, so this is now its notation. I can then work backwards and say, well, remember what we used before, n is just 3 minus 1, so it equals 2. So in this hydrogen 3 case, which we nicknamed tritium, it has 2 neutrons, whereas plain old non-isotope hydrogen has no neutrons. And so this is a version of our isotope. The next aspect is what we call a radioisotope. So the word radioisotope can be broken into 2 parts. Isotopes we've already talked about. That's just whether it's added or subtracted protons. This is not charged. This is added a neutron, or subtracted a neutron. So if we add neutrons or subtract neutrons, we get the isotope. Radio comes into the term of radioactive. So a radioisotope is an unstable isotope. Some of these isotopes you can find naturally, and they're perfectly happy to just have one more neutron or one less neutron. But if we add too many to it or subtract too many to it, we end up becoming unstable. So whether that's there's way too many and the nucleus becomes too weak to hold it together, and we'll talk about that a little bit later when we talk about what that means to be radioactive. But basically a radioisotope is an unstable one. If we look at the graph of the stability of elements, you can see this line. And the line shows that anything above it has too many neutrons, and that's now unstable and radioactive. And anything below it has too many protons, which could also come about by subtracting away too many neutrons. And so on both spectrums of that, we get these unstable or unstable elements, so we get this instability there, and that becomes radioactive. So radioisotope is a radioactive isotope. This notation, like hydrogen 13, cobalt 16, just tells you the mass numbers to indicate that they're not the ordinary mass numbers. And the mass number, the isotopes, just say it has more or less neutrons than it ordinarily would in its plain old form.
Tell me pretty lies, look me in the face, tell me that you love me, even if it's fake.